Very good. The recording has started. It is February 3rd, 2025, and this is the Western Automation Monday morning technical class. Today, we're going to go over the process of acquiring data and sizing gearboxes for several applications. The acquisition of data in any engineering exercise is important. Knowing what data to acquire makes your efforts more efficient, and we hope to help you accomplish that today. We don't need a lot of data to properly size gearboxes. There's so much commonality between applications. For example, the azimuth and elevation application, where you rotate horizontally in the azimuth axis and you elevate in the elevation axis, lifting, is used in many, many different applications, such as gun emplacements is the obvious one, large and small antennas, which is a huge market, all sorts of positioning gimbals that are used in a variety of applications, such as drones. And in that case, the ASL application may be a downward pointing device and therefore may be inverted. The azimuth elevation application is used to point something. The typical application for gearing is in motion control, conveyance, and lifting, either on a vertical or on an incline. And you will see that in many, many different applications. Learn the techniques for that, and you have a whole range of applications that you can apply them in consistently. So what we want to do today is introduce you to the information that you need to get assistance and to eventually develop your own capability to complete the sizing accurately and reliably. With that, I'm going to share my screen. This presentation I sent to you last night, and I'll resend it today because I did some things to it that I think are just some minor edits. Will somebody acknowledge to me that you see blue screen with gearboxes on it?
Yep, we see it.
Good. I always like it when things work. So, the concept of the target shaft. Let's not think about the gearbox, which may seem a little bit initially counterintuitive. We want to define the performance on the target shaft. And typically for us, the target shaft is going to be the output shaft of the gearbox. That's where our responsibility will end. The customer may drive something else with that. Well, obviously they're going to drive something else with that target shaft. They're going to attach it to chain and sprocket or some belts, or maybe directly drive the machine that they're designing, and they're responsible for the design downstream. Upstream, we're responsible for the design. And what's really important, especially if you're in the sales field, is that once you define the target shaft performance, you can then accurately specify all the components right on up to the three-phase power supply, or in the case of hydraulics, the hydraulic power supply, or in the case of air, the pneumatic power supply. Now that gives you accurate data to quote more than just the gearbox. You quote the motors, you quote the controllers for the motors, various sensors, any encoders necessary, etc., etc. So, in general, we want a speed-torque curve. If we know how the target shaft driving the machine is to operate over its speed range, and we overlay the torque requirements on that speed range, we have an XY axis. y being the vertical, x being the horizontal axis, a typical mathematical graph. And we can then compare the two and create a curve. From the x-axis, we typically, well, it actually goes both ways. It depends on your style. There's no right and wrong here, but torque can be on the x or the y-axis. Obviously, speed or velocity or RPM will be on the other axis. Now, once we have established the speed torque curve of the machine, well, then we want to know how often the machine runs. This is for sizing the gearbox and the other components based on thermal considerations, as well as some life calculations if you're doing that. Then we want to get into things like accuracy and repeatability of torque, velocity, and position. If it's a turntable, for example, and again, that's one of those ubiquitous applications, you know how to size a turntable, you can attack a lot of different potential opportunities. And turntables typically don't just rotate. Yes, if it's a car in a showroom of a dealership, maybe it just turns around and around and around. But a turntable in a dial plate application where you are moving from one station to the other station and performing operations on what's being carried on the turntable, and I'll be more specific here. Let's take pill bottle filling or powder filling into a bottle, be it glass or plastic. This is a very common application in pharmaceuticals. The dial plate carries initially the empty bottle around to different stations where it gets powder or pills filled into it. Then it gets a little piece of cotton stuffed in it. Then it gets capped. And nowadays, with all the security we have to have on our consumer products, then there's a seal that goes around it, which is sort of a labeling application. Then you get the actual label, whether you're lasering it, painting it, or actually sticking a label onto the bottle. And at that point, it may go to an inspection station, and then it's picked off and sent down and put in a box or however it's packaged to ship to the customer. That dial plate application, because it starts and stops, position is important. Torque and velocity can be important too, because we don't want to move so precipitously that we knock the bottles over. Yet we want to move as fast as possible to optimize and maximize production. But position. How accurately do we need to put that bottle in front of its station so it can be properly filled? Or the cotton stuffed in? Or the cap screwed on? Or the label affixed? We need to know that. And in an application like a dial plate, it's circular, and we would want to know that in terms of degrees, arc minutes, and arc seconds. So that's an application example of what we mean by accuracy and repeatability. Now, for those of you that don't understand the difference between accuracy and repeatability, I highly suggest that you get a deeper understanding of it, but for the purposes of this moment, accuracy is the absolute adherence to a target position. In other words, if you're on a dial plate and you need to turn that thing to 0 degrees straight up on the clock face, accuracy is how accurately you get to 0 degrees. If your accuracy is plus or minus 1/10 of a degree, then you're going to vary in position around 0 degrees. Repeatability is how often you get to the inaccurate position defined by accuracy. For example, if you have a very high repeatability, and let's say your accuracy is plus or minus, as I said, 1/10 of a degree, but your repeatability is really high, so you always land on plus 1/10 of a degree. You're within the accuracy range, but your repeatability constantly hits that. It doesn't get to zero. It doesn't get to minus a tenth of a degree. So a good example of another example to illustrate accuracy and repeatability is if you're shooting at a round target with a rifle, and the center of the target is the measure of accuracy. And the closer you get to that center of the target, the more accurate you are. However, if you're a good shooter, but your scope may be off a little bit, and you group your bullets 4 inches to the right of the center of the target, you have bad accuracy. But if those bullets are grouped within 1/4 of an inch, then you have good repeatability. Typically, repeatability is the important thing in most applications, because you can then adjust. In the case of the gun target, you just move the target to the right 4 or 5 inches, whatever the inaccuracy was, and now your grouped bullets are in the center of the target. Or what we usually do in shooting is we adjust the scope itself with the dials on the scope. So good repeatability means the machine is performing in a repeatable way, and then we can make adjustments to improve the accuracy to the degree that we need it to be. Standard environmental data, I don't really need to go over that too much. That's, are you dipping us in acid? Are you spraying us with mud? Is this operating in mil-spec temperature ranges, or is it standard industrial temperature ranges? Maybe it's in a very cold environment. These things you need to define. Now, a couple of basic formulas. Torque equals force times the radius around which the force is applied. Torque and force are integrally related, obviously. Force is a linear application of your effort. Torque is force applied around a circle. Pedaling a bicycle. When you pedal a bicycle, if you have really strong legs, you can put a lot of force on the pedals, but by definition, since your feet are typically attached to the pedals in some form or another, your force is going to be applied in a circle. The faster you pedal, let me back off on that, because now I'm digging the issue of power. So the radius around which you apply your force determines torque. Now, a greater radius, a longer pedal shaft, means with the same force, you're going to be producing more torque. And that is the principle of leverage. I think it was it Galileo or Da Vinci, one of those two, said that give me a lever arm long enough and an appropriately placed fulcrum and I can move the moon. And in this case, your radius is your length of your lever. So the torque to accelerate a load is different from the torque to drive a load. We calculate the torque to drive a load based on the consistent force and the radius that we're, and by the way, the radius will come clear to you as we start to go into gearboxes and ratios. The torque to accelerate the load is much more concerned with the inertia of the load. If I'm trying to accelerate a 4-inch shaft of steel 10 feet long, then I'm going to get a certain torque required for that. However, if I'm trying to accelerate a 10-foot long shaft of steel, but instead of 4 inches, it's 4 feet wide, in other words, the diameter is 4 feet, then I'm going to have hugely more torque required. And it's not going to be 12 times more, 4 inches to 4 feet. It's going to be the square function. The wider your load is dispersed on a radius centered around the shaft that you are turning and applying the torque, the greater the torque to accelerate that load. Once you get that load to speed, this second formula goes away, and we're now back to the first formula. But this second formula can be very limiting in terms of sizing the gearbox, especially if T is very small, because you can see T is in the denominator, and therefore it's inversely proportional to torque, which means the higher T is, the lower torque is, which translates to the longer you have to accelerate a load, the lower the torque required to accelerate. The shorter the amount of time you have to accelerate the load, the more torque required. Drag racing is a classic example. If you need to get to the quarter-mile point as fast as possible, you're going to apply the maximum torque. You're going to have a monster engine. And that engine is way oversized if you just want to run the car at steady speed. Now, obviously, most of our cars are not like that. But the fact is that the acceleration time is what often becomes the limiting factor in sizing the drivetrain of which the gearbox is a part. And therefore, the running torque is pretty much covered because of the fact that you have to get to speed very quickly. Now, let's talk a little bit about the vertical lift application. The vertical lift application is really a great one to talk about first because it's so easy to calculate. The force is basically the weight hanging at the end of a cable. This green circle here represents a drum. So we have a cable drum. And turning the drum winds up or winds out the cable, therefore raises and lowers the load. And therefore the torque required to raise and lower the load is the force, which is the load itself, and the radius of the drum. Very simple, very straightforward, and allows us to easily calculate lifting applications. Typically, there are no other factors involved. Now, we can get crazy and say, okay, sometimes the load is underwater. Well, okay, now we have the resistance of the load to the fluid. If there's a downdraft, well, I've never had an application like that, but theoretically that would put some downforce on the load itself, depending on the profile. And we'd have to calculate the force of the downdraft on the surface area of the load. But the bottom line is, this is very simple. This is the weight times the radius. Now, if we incline that, now we get a whole different story. Because we're not directly lifting. We're dragging it up an incline. Now, when they built the pyramids, and they brought those huge stones in from the quarry, they didn't just lift them into place. They used ramps and drug them into place. And thus, this application formula was in effect in terms of the physics of that action. We have, again, our weight. We have several force vectors, which you don't really need to be concerned about. I'm just going over them to give you the idea of the physics. But this force vector is perpendicular to the direction. Here we have the force vector in the direction. Here we have the force vector against the direction or the lifting incline. And then note, we have a red vector, which is the sum of the whole thing. Now, let's get to an easy way to calculate this without getting too deep into the theory of the physics behind dragging things up an incline. But again, here we have this vector here, which is in the direction of travel up the incline. That force vector, isolated, is your friction coefficient. Now, in air, lifting vertically, we can negate that. Like I said, we don't have a lot of windage unless you're in a fluid. But on an incline, you're dragging something. Now you're on wheels maybe, or maybe you're on rollers. That would give you a lower coefficient of friction. But in this case, you can't ignore the coefficient of friction. It's significant enough that it has to be part of the calculation for torque required to lift the load up an incline. This is the opposite of the friction coefficient. Obviously, going down the ramp, you still will have some resistant friction. This is the force to, well, how do we say that? Okay, these are perpendicular to the direction of travel. And they are force vectors. You're going to have to apply force Fn in order to move up the slope. But again, we're getting a little bit too deep in the weeds here in terms of the physics of it. Let's go to the meat of the matter. This angle here is called theta. It's a Greek letter, just consider it a symbol. Whatever this angle is determines the amount of force to drag this load up the incline. In the case of this incline being vertical, in which case it's this, then it's 90 degrees. Anything less than 90 degrees. Now, the sine of 90 degrees, that's why we use the sine function. It's a trigonometric function. The sine of 90 degrees is 1. So if we multiply the torque required in this particular case by the sine, we get the same amount of torque as if we have the load and the radius. Everything less than 90 down to 0 is going to require less force to lift the load, therefore less torque to lift the load. And that makes sense, right? If we're level, the sine of the angle of 0 is 0. And therefore we have no lifting vectors whatsoever. All we have is the coefficient of friction. Now, I'm going to just click on this to show you if it works. Maybe This is a great little video to explain this further. We're limited in time here. I'm going to have to move on. Oh, crap. I didn't want to do that. It's interesting. Today I had an update on my computer, and I use DuckDuckGo for my browser, and it had completely wiped it out and put Google back in place. Okay, so this is the stickman physics. There's a nice little video here. We don't have time to play it, but that link is on there if you want to go to a more precise explanation. And I realize that, frankly, my explanation this morning was kind of crappy because I haven't had much coffee yet. Nevertheless, the summation of this is that in the lifting application, if you're going vertical, you're full on the force. If you're going horizontal, if you're going horizontal, you have no lifting force, obviously. Then you just have coefficient of friction. And if you're anywhere in between, you're going to be somewhere between 0 lifting force and full lifting force based on the sine of that angle. And the sine of the angle from 0 to 90 degrees varies from 0 to a half up to full for vertical. Now, the next thing we want to do is we want to define the velocity profile. And the velocity profile is very simple. You have an accel, you have a run at speed, and you have a decel. If you're running from point A to point B as fast as possible, you will have no TC because you're going to accelerate as fast as you can, and then you're going to start decelerating right away. But that still qualifies as a velocity profile. Now, if we overlay torque onto the velocity profile, you can see that during the acceleration, remember, that acceleration torque took into account the inertia of the load. So typically, you're going to have a very high acceleration. If this is a horizontal application, your torque required during the constant speed running portion of the velocity curve will drop down to what essentially is the coefficient of friction dragging that load across the surface. And then when you want to decelerate it, your inertia comes into play again, and your torque increases appropriately, but in the negative direction, because we're taking the kinetic energy out of the load, we're decelerating. So that's very simple. Therefore, we have, well, okay, let's say that this is accelerating a conveyor to speed, and the TC portion of it is 8 hours because the conveyor runs all day long. But we accelerate it and we decelerate it at the beginning and ending of the shift, respectively. Then we have to concern ourselves with 2 regions of performance of the components that we select. And every component, whether they put it on the nameplate or not, is going to have a continuous duty performance and a limited duty or peak performance. And remember, we're talking about the torque right now. It's the size of gearbox. So the continuous duty region is the torque that I can apply or transmit through that gearbox 24/7. And it runs just fine, and the lubrication does its job, and the gears don't wear out too fast. And the thermal aspect of the gearbox is such that the gearbox runs within its acceptable temperature limits. And the mechanical aspect of the gearbox is that I don't break off teeth and I don't wear them too fast. Once we get into the limited duty region, here is where the unit heats up too much to run continuously, or we're stressing the mechanical components too much, such that it will not run continuously. But it will give us limited duty performance, such as accelerating to get to speed. Now, the limited duty region is a declining formula. The closer you are to the continuous duty region, the longer you'll be able to run. When you're up here at the maximum level of torque transmissibility through the gearbox, note it says maximum instantaneous torque. Go beyond this, you break the gearbox. You overheat the gearbox. You trash the seals, whatever. Okay? So we are, again, torque on the y-axis, speed on the x-axis. For those of you that were trained to have speed on the y-axis and torque on the x-axis, you have my apologies. Now, this is a trace off of a Beck-Off data collection system on a application I did recently. And there you have several different curves that you can look at the same time to get a better idea of what this movement exercise is. Here you have the movement from position A to position B, and you can see we're doing it in a relatively smooth fashion. Note that the velocity here, this is a point A to point B application. We don't run at constant speed. We just want to get the point from point A to point B. So we went to our maximum speed and started to decelerate. Here is our acceleration, obviously up to the point where we start deceleration. It's positive, then it goes negative. And the torque, look at that, it's constant. Interesting. Now, this means this is on a horizontal plane. and we didn't have a significantly high differential coefficient of friction or anything that was different between accelerating the load and decelerating the load. And therefore, you have torque constant. However, just to illustrate the point, if we had a large flat surface perpendicular to the velocity direction or the movement direction, and there was a huge wind, well, then the torque on this side of the movement curve would be higher, and because the wind helps to decelerate the load, it would be lower on this side. Now, wind acts very similarly to friction. So obviously in this application, there was no significant amount of friction in moving the load, probably on some very nice ball bearings and wheels, and therefore not a significant difference between accelerating and decelerating. With a high coefficient of friction, it would resist acceleration and it would assist deceleration. Therefore, this horizontal constant torque curve would be higher in the first half and lower in the second half of this positioning move. Now, when we talk about gearing, we talk about reduction ratios. We talk about gaining mechanical advantage at the expense of speed. So, multi-stage reductions consist of several reductions within the gearbox. The total ratio is the product of all the stages. So if it's 2 stages, it's the first stage times the second stage, 3 stages, etc., etc. In this particular case, we have a ratio of 1.84, 2.47, 2.57, and the total is 11.68. Sorry, those commas were because this was aimed at a European audience. When it was originally drawn in Europe, they use a comma where we use a decimal point. And my apologies there. Now, the role of gearing in applications, as I said, gearing reduces the speed, the velocity, the RPM, but it multiplies the torque. So it's a quid pro quo relationship. You get something, you give something. And gearing can reduce the cost of achieving the desired performance on the target shaft. That's why we use it. If you had to direct drive everything with the motor, sometimes the motors would get huge. And they would have to run at very, very slow speeds, which means they would have to have multi-pole designs. The typical motors we use are around, on the industrial side, we're going to use induction motors, and they're going to be typically 4-pole motors, so we hit 60 hertz power into them, and they run at 1800 RPM. But what if I want to run my load at 100 RPM? Well, then I've got to have a motor that instead of 4 poles has 4 times 18 is 72 poles. My God, that thing would be monstrously costly to manufacture and dramatically inefficient compared to the 4-pole motor. Thus, gearing. There are some negative sides to gearing as well. There are many applications that are direct driven with extremely expensive motors. A lot of them being in the higher accuracy range or in the range where we want extreme compactness. Robots, for example, many of those are direct drive axes, but a lot of those also have gearing. So gearing, in most cases that you're going to run into where you want to run a load at a certain speed and a certain torque, gearing or some form of mechanical reduction, belts and chains is another option, you will find that they are useful, economical, and appropriately applied to achieve the optimum solution. Now, considerations using gearing in applications. A lot of these don't matter. We really want to talk about some of them when we're doing precision motion, especially the first one. What does that mean, nonlinearity? It means that, let's say it's a 10-to-1 reduction. Therefore, I turn the input shaft, which is the motor shaft, 360 degrees, and the output shaft turns from 0 to 36 degrees because of the 10-to-1 reduction. Now, if I move the motor shaft half a revolution, therefore move it to 180 degrees, does the output of the shaft of the gearbox perfectly move to 18 degrees? And that's the case of linearity. In many cases, it doesn't. Because of the geometry of the teeth of the gearbox, etc., it may, backlash is another issue, it may land on 18.1 or 17.7 degrees. Therefore, it's nonlinear. It's not perfectly matched up to the input motion. That nonlinearity isn't acceptable in many applications. Does it matter in a conveyor where you're always going in one direction? It really doesn't. So a lot of these have greater or lesser importance in the applications that we're discussing. Talked about backlash. That's where there's space in the teeth of the gearing, and therefore, if you're driving in one direction, the backlash is such that you're always pushing on one side of that tooth gap. If you reverse, there's a point of no motion because the teeth are moving between the gap, and then you hit the reverse side of the gearing interface and you start to apply torque again. That zero motion, lost motion section is the backlash. In most cases, that doesn't matter. In precision applications, it usually does, and you have to define it. There's another case where backlash can be quite deleterious, and that is when you're doing high cycling applications, because you're driving in one direction and then you're slamming it into the other side of the gearbox gap, and that you accelerate across that gap and hit the other interface with quite a degree of peak force. And you keep banging those gears back and forth on each other, and eventually you're going to wear them out and break stuff. The application that comes to mind that I was able to apply a precision gearbox in what was normally a standard gearbox application happened to be on a piston pump, where it was part of a compressor design, and the piston, as you know, is a linear thing, so it compresses and then it releases and compresses and releases, and it's driven by a crankshaft, and that crankshaft was driven by my gearbox and then my motor. Well, when you turn this thing on with a high backlash gearbox, you heard a cacophony of high frequency rattling that we were able to trace directly to the cycle frequency of the pistons. And we realized that the pistons moving back and forth were slamming on either side of the backlash of the gearbox and making this chatter. I applied a high precision planetary with a low backlash, and the thing just quieted out. So there's an industrial application where precision gear saved the day, basically. I've had that business now for 25 years. Now, there are also efficiency factors with gearboxes. As you know, you have X amount of horsepower going out of your motor, and how much horsepower do you have down on the final shaft of the gearbox? The difference being the efficiency. That begs the issue of thermal performance of the gearbox. The less efficient the gearbox is, the more it's going to heat up. The less continuous capability it thus has, or the more cooling you're going to have to put into that gearbox, like fans or breathers on, or radiators on the oil, etc. Gearing reduces the mean time between failure of the total system. Why? You're adding more parts. It is a mechanical device. It has all sorts of things that wear out, like the bearings, like the teeth, the fluids that you use to lubricate and cool it. And gearing definitely requires maintenance. Seals wear out. Lubrication has to be changed. In many cases, you're going to have a periodic maintenance where you're switching out the bearings, etc. So now, this is an important piece of data as we start to move through the basics of this. What is the maximum ratio per stage? Why do you want to know that? Because in some applications, you have high reduction ratios required. like that application I talked about a moment ago, which was 1800 RPM down to 100 RPM. That's an 18-to-1 reduction. In many of the gearboxes that are up here, you'd have to go 2 stages. That's more cost. It's better to use a single-stage gearbox versus a multi-gearbox, notwithstanding other factors. Note, worm has a very high reduction ratio relative to the other options. Hypoid is a type of worm. Cycloidal and harmonic gearing, we went over in a previous class a couple of weeks ago. Those are very specialized types of gearboxes. We're not going to focus on those too much today, but later on in this presentation, for those of you that missed the previous class or want to review it, there is a video, there's links to videos that show you what cycloidal and harmonic gearing are. And yes, they are very compact, have very high ratios. They also happen to have zero backlash. These are very special gearboxes. They're also very expensive, but when you need them, you need them. Now, this is the maximum ratio per stage. It's one aspect of choosing the gearbox to satisfy your 18-to-1 ratio. In the case of a spiral bevel or a helical and spur gear, I'd have to go 2 stages, 6-to-1 and 3-to-1, 5-to-1, and whatever 18 divided by 5 is. In the planetary, I would have to go 2 stages. But I could do it in 1 stage on a worm handily. Just another factor involved here. By the way, and I'll add a little note down here at the bottom when I send this updated presentation to you. These are ratios that I personally feel are the application limit where you're on the correct side of the point of diminishing returns. For example, if you go beyond 8-to-1 in a planetary, it requires derating because the planet gears get too small to transmit the torque at that high reduction ratio. You have a similar issue with spiral bevel. And when I show you the geometries of the gearboxes, if we have time today, you'll see what I mean by that. These ratios are on the positive side of the point of diminishing returns. A lot of companies sell 10-to-1 planetaries, but you have to derate them so much that they're almost as costly as using a 2-stage planetary with appropriate ratings and avoiding the heavy derating. Now, worm gears, one of the disadvantages of worm gears is that they're not as efficient as other gears. The planetary gear, for example, it would be would have the helical efficiencies because it's a helical style gear, albeit in a planetary layout, is going to be 94 to 98% efficient. But look at the worm. The worm can be as low as 50% efficient. Why is there such a wide range of efficiencies on a worm? Primarily because, as I'll show you in a moment, some worms have 1 tooth of contact. They're cylindrical worm gears. And then there's a technology called double enveloping worm gear where you have 4 teeth of contact, which is obviously more meat in contact, so you can transmit more force. But tooth pressures are less, and in worm gearing, tooth pressure is directly related to efficiency. And since you're moving the force through the gears on more surface area, your sliding friction is less, therefore the efficiency is higher. So these are the general efficiencies. I will caution you that if you assume everything is 95% efficient, you're going to get in trouble, especially if you use worm gearing. And there's one other aspect of worm gearing you need to be aware of. On a spur, a straight bevel, a planetary, which is the same as helical in this efficiency chart, your efficiencies are consistent throughout the speed range. That sink in for a little bit. Worms are not consistent throughout the speed range. Their efficiency degrades the lower in input speed you go on the gear set. Makes them a little bit more complicated to size. They require high starting torque because of all that sliding friction of the surface area of contact, which makes worms so robust and so so capable of taking brute force. However, they have the disadvantage of very low starting torque. And that starting torque ramps up to the optimum torque required at operating speed. You have to take that into account when you use worm gears, and that's what this slide refers to. The other thing about worm gears, and it's an advantage or a disadvantage depending on the application, is that they have a very poor back driving efficiency. Some people call that lockup. It's not lockup. Don't ever assume a worm gear is going to consistently lock up in the reverse direction. In the reverse application of the load. And let me take a moment here to define that. Back driving efficiency. We are always going forward in the current discussion in this moment. The difference is that I'm applying motor torque, positive motor torque to move forward, versus the load is applying torque back against the motor. We're still going in the same direction. An example of that is driving a load up a hill, in which case we're going forward and the motor is applying torque to the gearbox, and we're getting the efficiencies of the worm gear as published. When we go over the top of that hill and start going down the other side of the hill, the load is now pushing torque back against the gearbox. The motor is in negative torque or regeneration mode, resisting the free fall of the load while still controlling the velocity. When the load pushes back against normal gearing, the ratios are the same. So if you go over the top of that hill with a helical or a planetary gear set, the motor's going to do all the work to resist the load accelerating to free fall. In the case of a worm, because of its poor back driving efficiency relative to its forward driving efficiency, the worm gear is going to absorb a lot of that force of the load trying to accelerate based on the gravity of the downhill side of the hill. And then the motor doesn't have to do as much work. If you make the ratio of the worm high enough, in some cases, it'll stop the load because its back driving efficiency is that poor. It can be 5%. The reason we never, ever depend upon a worm gear as a braking mechanism is because with any vibration whatsoever, that back driving efficiency may change and the load will inch down. And that's unacceptable in many cases. It can be quite dangerous. So you always should add a brake when you want things to stop. Nevertheless, you have to be aware that worm gear efficiency has two factors that other gearing doesn't have. One, it's not linear to the speed. It actually, the efficiency goes down the slower the input speed to the gearbox. And it has a very high starting efficiency, or starting torque required as a result of its poor starting efficiency. And in the back driving mode, it has a very poor efficiency as well. That can be an advantage or a disadvantage depending on the application. Now, we talk about gear teeth, and this is too much detail, but this is a diagram of what mechanical engineers understand as this is called an involute shape of a gear. There are some gear teeth that are round, cycloids. Involute is by far the dominant shape of gear teeth. We're coming up on 7:54, and I'm going to have to cut this class short at 7:58 because we have something we have to move to today at Western Automation, so I apologize. And what I may do is I may continue this class next week. So here are the different types of gearing depending on the geometries of the teeth. Note that in this picture, these are all involute shaped teeth, whether they're straight in the case of the spur, whether they're angled in case of the helical. Now, this gear to this gear, why'd they change the angle? Well, this is much quieter. Here's a double helical called a herringbone gear. This is used on many large gearboxes, and it tends to center one gear on the other gear as you're driving the torque through it. These are all inline gearing technologies. When you want to turn the 90-degree corner, you go to a right angle technology, which would be this, 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 and the worm gear. This gear here, which is a bull gear on which is a pinion on a bull gear. This one's internally toothed. You can have externally toothed as well. That's also still a linear technology. Very common here, by the way, on turntables and slewing drives. This is a rack and pinion. It's for linear motion. It's turning rotary motion into linear motion. In the inline technologies, we don't turn anything. We don't change direction. We just transmit torque in a linear, in a straight line. In these cases, we turn the 90 degrees. In these cases, we turn rotary torque to, or rotary motion to linear motion. Now, note your ratio on this type of gear is the diameter of this to the diameter of the driven gear. Similarly here, this is a 1-to-1. Miter gears are very often just 1-to-1. All they're there for is just to turn the corner. And as opposed to a spiral bevel gear, this is a straight bevel gear. It's basically the same thing between spur and helical. This one doesn't run quite as quietly as that one. But again, you're turning the corner. The ratio is the diameter comparison. In the worm gear, we have a totally different geometry. Note, this is one of the unique geometries in gearing. Let's go to this. There is a straight worm, and here is a worm with a bevel in the worm itself. In a straight worm, you're going to have the mathematical principle of a line contacting the circumference of a circle at a tangent point, which is by definition 1 point. Therefore, this is a one-tooth interface. Here, all the torque is transmitted from the driven shaft, or sorry, the driving shaft to the driven shaft in terms of one tooth. This is the worm, and this is the worm wheel, or worm gear. A little bit of trivia, this is typically steel. This is typically some specialized bronze alloy. Many worm companies claim that they have a very special bronze alloy. Cone drive does, and in some cases it has an advantage. In some cases it's just sales baloney. The driven worm, the driving worm, the driven worm gear. Now, we have between 4 and 8 teeth of contact, depending on the ratio, in a double enveloping worm gear versus a straight worm gear. What are the advantages and disadvantages? And I'm going to close on this because we're running out of time. This used to be much less expensive to manufacture, and therefore had a huge advantage in cost. It did not transmit near as much torque. Typically, you can transmit 30 to 50% more torque and much more peak torque because of the surface area of the teeth. You got 4 teeth in contact versus 1. Efficiency here, usually 10 to 15 points higher than a straight worm gear set. The cost advantage of machining this has gone away with the advent of 5th axis CNC, which happened 25 years ago, such that if you're making enough of them, this technology now can be very close to the cost of this technology. And as such, you still get the manifest benefits of more torque, higher peak loads, greater efficiency, and you're darn near the cost of the straight worm. This means that this is a technology to consider. And we want to bust a lot of myths because there's still a bunch of people that are out there thinking, oh, poor efficiency, oh, poor starting torque. You know, that is not true with the double enveloping worm. And if you carry those myths forward, you will not do yourself good service. So we are going to end with that discussion on the worm gears, and we will pick this up next week. But those of us at Western Automation have to jump to another meeting, and it's an important one. So I apologize, but it's 7:59 and we're all going to go to work. And I wish you a great week, and we'll see you next week.
Thanks, Pierce.